So this is my keynote lecture on the scientific revolution. It is the final topic in our Unit 2 for AP European history. So let's take a look and see what was so revolutionary about the science of this time. Well, prior to the 17th century, all science, or what they called natural philosophy, was based on established authorities, and these tended to be the ancient Greek natural philosophers, most notably Aristotle, but also the Greek astronomer Ptolemy. Okay, uh, it's a method rather of deductive reasoning versus inductive reasoning. We'll talk more about that in class, and I have a few slides in this too. But if you think about it that way, I think that's the best way to approach your reading of Palmer and your study of the scientific revolution. One is that it's a matter of how the science was done, not necessarily the invention of science. Science existed before the 17th century. It's a matter of how was science being done that makes it revolutionary. And to really appreciate that, you want to think of this issue of deductive reasoning versus inductive reasoning. Let's go to our next slide and see what I mean. Here's an example of deductive reasoning. In the ancient world, the Greeks thought everything a combination of the four elements: earth, wind, fire, and water. Now, these four elements occupied different levels in the heavens, different levels in creation. So, for instance, Earth, because it's the heaviest and the most dense of the elements, is at the center. It's under our feet, right? Um, and so Aristotle, the ancient Greek natural philosopher, he reasoned that fire, because fire was the lightest of the elements, burned upward because it sought to return to its natural state of rest, which is way, 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 way up in the sky. Okay, so that's an example of deductive reasoning. He's starting with a general assumption that fire exists up in the sky, and therefore works backwards to explain why it burns up. Okay, and so that's an example of deductive reasoning. Now, scientists in the 17th century, by that point, had invented something called a vacuum chamber, which was a device that could suck the air out of a glass jar or dome, and experiments could be conducted on that. Okay, and one of those experiments is that they would put candles in there and remove the air, and notice that the candles went out. So scientists in the 17th century realized that fire was a chemical reaction with the surrounding air. And through inductive reasoning, proceeding from that observation and then forming a theory rather than deducing, working from the general and going back. The scientific revolution is marked by a change from this deductive reasoning, which is making general assumptions and working backwards, to one of inductive reasoning, which we call the scientific method. It's experimentation based on observation. So Sir Francis Bacon, an English natural philosopher, is credited with being the father of the scientific method, which begins with observation. Okay, we form a hypothesis, we experiment, we analyze the results, and if everything works smoothly, we go ahead and publish those. Let's go on to the next slide. One of the pressing issues in the 17th century was actually about the location of the Earth. People already knew that the Earth was round. That was no longer an issue. Okay, everyone knew it was round, but no one knew quite where it was. Some thought, well, is it at the center of the solar system, or is it moving around the sun? Now, based on our observation, it seems natural to assume that the sun is moving because, look, every morning we see it rise in the east, we see it set in the west, right? Well, it was Nicholas Copernicus, or his Polish name was Nikolai Kopernicki, and he was a Polish astronomer, and he was the first in the 17th century to question the accepted Ptolemaic model of the heavens. Now, Ptolemy was an ancient Greek astronomer, and he believed that the Earth was at the center of the heavens, and that the sun and all the planets and the stars moved around the Earth on these perfect crystal spheres, perfectly round crystal spheres that rotated around the Earth. Okay? Now, Copernicus, the Polish astronomer, never published any kind of statement to the effect that the Earth moved around the sun. All he did was put forward the question, could it be possible? Okay, because if he had come out and said that the Earth moves around the sun, that would have contradicted the accuracy of the creation stories in the book of Genesis. And because in the creation stories, where we read that God created the earth and the first day of creation, and he did not create the sun and the moon until the fourth day. So therefore, the sun and the moon must be created outside of the earth. Let's go on to the next slide. Copernicus was followed by Tycho Brahe. He was a Dutch astronomer who withdrew his full support of the Copernican model. In other words, the sun-centered model, Copernican model. Following Tycho Brahe, Johannes Kepler, a German astronomer, suggested that the planets move not in perfect spheres around the sun, but rather in elliptical orbits. In other words, at some points around the sun, they are very close to the sun and sometimes far away. Okay, so an ellipse. But Kepler, like Copernicus, lacked the mathematics to prove his theory. It wasn't until Galileo that the first true publishing of a sun-centered theory appeared. Galileo was a professor of mathematics at the University of Pisa, and he published on the movement of the heavens, the starry night. The Starry Messenger was his publication. And it caused Pope Urban VIII, who was an acquaintance of his actually, to have him excommunicated and place him under house arrest. Okay? Now, contrary to popular belief, the whole issue with Galileo was not just a matter of Galileo versus the Catholic Church. This was Galileo also against the scientific community. Galileo made just as many opponents, had just as many critics from among his fellow scientists as he did from the church. And contrary to popular belief, Galileo also had supporters from among the clergy. Okay, so it wasn't just a black and white cut and dry thing. The criticism that was being thrown at Galileo was that he was doing sloppy science. Remember what I said in the first slide, that the scientific revolution is about how the science was being done, not necessarily that science was created in the 17th century. It was a matter of how was it being done. And so the criticism thrown at Galileo was that he was doing sloppy science. He was not doing science the way it had always been done before the 17th century. He was not proceeding from general assumptions down to the particulars. He was doing it backwards. And even his fellow scientists were critical of him for this. Okay? So let's take a look and see now what it was that Galileo was doing. First of all, Galileo did not invent the telescope. The telescope was invented by Arab astronomers early in the Middle Ages. But he did use his scope to observe the moon, as well as the sun and the planet Jupiter. Now, what he saw caused him to question, based on his observations, mind you. Notice that importance of observation. Based on what he saw, on what he observed, it caused him to question the previous theories of the ancient Greeks. Okay? For instance, the moon was thought to be a perfectly smooth sphere, made up of this kind of magical material, this perfect material. When Galileo looked at the moon, he saw craters, mountains, and valleys. So it's obviously not smooth. And it's obviously made of solid material. Okay? When Galileo looked at the sun, he saw sunspots, also showing then that it was not perfect. Okay? Finally, Galileo observed 4 of Jupiter's moons, all moving around the planet over several days of observation. Okay? Over several nights, I should say, of observation. Galileo observed 4 of Jupiter's moons moving around the planet. Now, the previously held scientific notions equated movement with imperfection. In other words, based on the ancient Greek model, anything that was moving was not at a state of rest, and therefore was in a state of change and was imperfect. Movement meant imperfection. Okay? And so the previously held notion was that when something is at a state of rest, it is perfect. When something is unchanging, it has reached perfection. So, it stands to reason, if God created the heavens, then they must be perfect, and therefore there can't be anything moving around other objects in the heavens, right? That was the notion. But Galileo, like Kepler, lacked the mathematics to prove his theory. See, the math that Galileo had available to him was basically geometry, which is fine if you want to determine the height of a flagpole or a fence post, but it fails to account for movements of planets around a star. You know, you can't use geometry for moving objects. It only works for stationary objects. What Galileo needed was a body of math, a discipline of math that could deal with movement. And that body of math would be invented in the late 17th century by the English scientist Sir Isaac Newton. We call that body of math calculus. And that will be the topic of our in-class lecture for our next class session.